Physical Sciences session. My name is Temba. Today we are looking at introduction to a very special type of reaction that are, very important in our chemistry, which are the redox reactions, right? We shall try and look at, what happens, when simple substances, in reactions, they form new substances, and then we try and check exactly what happens in terms of, the electron at an atomic level, in terms of electrons, in a typical redox reaction, right? Okay, so our focus for today is on oxidation numbers, okay? That's our main idea, which will form, the greater component of our discussion, right? But this is in the context of redox reactions, right? Okay, so the thought that's going to guide us today, or something that we need to think about as we go through our session or discussion, is that what exactly happens when oxygen reacts with other element. Take note, this is in the context of reactions. What happens when oxygen, not just to oxygen, when different elements react with oxygen, what exactly happens? So that's the big question that we want to put out there, right? Okay, some of the terminology or the key terms that we will make use of for the purpose of our discussion today, the following phrases, electron rich or electron poor. So it is about the electrons, right? Then the other key term is oxidation number. Okay, we'll try and understand what oxidation number is all about, and we'll try to make practical examples in terms of how exactly you go about in determining, or assigning oxidation numbers to different elements within a compound or, a polyatomic ion. And then we'll also look at electron transfer. So if we talk about transfer, exactly, it means there must be one thing that loses while the other one gains to facilitate that transfer from one, species to the other, right? So these are some of the key terms. Okay, now in the background, what is it that we understand? We know that during chemical bonding, atoms of elements have different arrangement of electrons, right? This actually goes back to, the basics, the fundamentals of chemistry in as far as the periodic table, to say when we talk about electron configuration, we're simply saying that it is specific to a type of element, because an element, is a substance that is made up of a particular type of atom, okay? So same atoms, they make up an element, but once these atoms combine with each other during chemical bonding, we can form, other molecules of elements or molecules of compounds or formula units. It takes us way back to chemical bonding. So that knowledge that we have, we need now to bring it forward and try and see how it fits into the bigger picture in as far as oxidation numbers are concerned, right? So we are saying that when atoms join together, this is during bonding, okay, to form molecules or a network structure, right? So molecules will be via your covalent bonding, and then network structures, or crystal lattices with your ionic substances. Electrons are actually transferred or shared. So this is very, very important. The transfer of electron in the formation of formula units during chemical bonding is what ionic bonding is all about. But then the word core means sharing. So if we talk about covalent bonding, it essentially has to do with the sharing of electrons that occur at the highest energy level, the valence electrons between atoms. But why do these atoms bond with each other? I think we'd remember very well that this has a lot to do with actually, the stability, because they need an electron configuration that resembles that of group 8 elements, which are noble or stable gases. So that's the big idea. So we want to try and develop an understanding of oxidation number based on what we already know. Hence, it's very important for us to remind ourselves of chemical bonding, right? Okay, and then atoms that donate electrons are electron rich. Okay, so those that donate electrons are electron rich. It means they've got a lot of electrons, right? And then those that actually take electrons are electron poor. So for rich or for poor, but in the context of transfer, in the context of losing and gaining, this has to do with electrons. We're not talking about protons at this point in time, because we know in terms of, the atomic structure, the basic unit of an element, the atomic structure, we know that electrons actually occupy the energy levels, or the shells, which would alternatively refer to as the orbitals, okay? So hence we talk about loss or gain of electrons. It's very, very important for us to remind ourselves of that, okay? And then oxidation number, which is our key focus for today. What is it all about? So when we talk about oxidation number, the oxidation number of an element, this is for an element, okay, is a number assigned to keep track of electrons during a chemical reaction. Now, in the context of chemical reaction, there is loss, there is gain of electrons. Oxidation number of an element in a compound is actually the measure of the richness or deficiency. So richness, it means electrons have been gained. Deficiency, electrons have been lost, okay? So that's the understanding. And then oxidation number can either be positive or negative, right? What do we mean by that? We're saying that a negative oxidation number indicates that electrons were pulled towards an atom in a compound, okay? And then while a positive oxidation number tells us that electrons were pulled away from an atom, right? Okay, so in a compound or an element, there are two types of oxidation numbers. We've got a unit oxidation number, okay, which has to do with an element, and the total oxidation number, which has to do with a compound, or it has to relate to an element, where it has got more than one. But hence, focus is on total and unit, right? Okay, so if we talk about the unit oxidation number, it is written above the symbol of an element of a compound. Now, if for argument's sake we look at the unit oxidation number of sodium, sodium is in group 1, so its unit oxidation number is +1. But because in this compound of sodium oxide, what is happening, there are 2 sodium atoms, then the total oxidation number for this element is +2. Okay, hope it makes sense. And then the unit oxidation number represents the oxidation number of one atom of the element, in this case, which is +1. But what about the total oxidation number? Total oxidation number actually represents the number of, the total, of an element in a compound. Why do we have this +2 as the total oxidation number? Because there is 2 times +1, which is the oxidation number, which gives us the +2. So this +2 is actually our total oxidation number for sodium, right, in this compound, right? And then how do we assign? Oxidation numbers are similar to the valence electrons, and these valence electrons actually the number of electrons that occur at the highest energy levels. So there are a list of rules that will actually help us to assign oxidation numbers to elements. So what's going to guide us in this case are the rules, which is what is something that will focus our attention on. Right. So having said that, what's the main idea that we take in this segment is that we talk of electron richness and electron deficiency, and then also that has to do with the unit oxidation number of an element, or an atom of an element within a compound, as well as the total. But then after break, what we'll do, we'll try and make practical examples to try and understand the difference or the link between unit oxidation number and total oxidation number, in as far as applying these rules of assigning oxidation numbers to elements. Let's take a short break for now. Welcome back to our session. We're still talking, the rules in terms of assigning oxidation numbers, to elements within a compound. We shall also take a turn to try and look at, polyatomic ions and use these rules. But essentially, let's try and understand how these rules are actually applied, okay, in making use of, the chemical substances that are given. So these rules are what is going to be important moving forward. So you need to pay careful attention to this. Right, so we're still discussing oxidation numbers. Right, now the focus now is on the rules for assigning oxidation numbers. So the abbreviation ON will be for, from now moving forward, it will stand for oxidation numbers. Okay, take note of that. So the first rule says the oxidation number of an atom of an element is 0. Right, let's break this down. If we've got an atom of an element in its natural state, it means it contains the same number of positive charges and negative charges. So the net charge, which is actually the oxidation number of this atom of an element, which is a pure substance, is equals to 0, right? That's the first. So if you are given an atom of an element in its natural state, you'd realize that its oxidation number is equals to 0. So that's the first rule in terms of assigning the oxidation numbers. Okay, right. So let's take, for argument's sake, we've got sodium as a pure substance. The unit oxidation number for this atom is 0. So is the total oxidation number. Okay. Say, for argument's sake, also we've got a molecule. This is an atom of an element, right? This is an atom of an element, take note. While on the other end, we've got a molecule of an element, right? Okay, you need to distinguish that, right? So in this molecule of an element, these are two atoms of the same kind, hence we are saying it's an element. Okay, so it exists as a diatomic molecule. So the unit is 0. The unit oxidation number is 0, and the total oxidation number for this molecule of an element is also 0. That's the first rule. Right. Let's go to the second one. It says all, emphasis is on all, uppercase, capital letters, all group 1 metals, which are alkali earth metals, have an oxidation number of +1 in combined state. Well, there's a lot of information on this. Okay, now we are saying group 1 metals. That's your sodium. Okay, that's your potassium, that's your lithium, okay, as examples. So the groups of elements are actually these vertical columns, okay. So elements within group 1, all of them in their combined state. Combined state, what exactly are we talking about? When they're in compounds, when they have bonded with other elements to form compounds, right? Their oxidation number is +1. Okay, that's what the rule says to us. Okay, we can take, for argument's sake, in this case, sodium. Sodium has a unit oxidation number of +1, okay, the one that's written in red. And also, in this case, the total oxidation number for this sodium atom is also +1, right? Again, in a different, this is another combined state of a group 1 metal, which is sodium. The unit is +1, and then the total is +2. So in other words, what we are saying, we are saying that there are 2 sodium atoms in this combined state. So if we say if the unit is +1 and then there is 2 of them, then the total is +2 in this case. That's how we obtain this +2. But we are saying that the unit, oxidation number of any group 1 metal is +1. Okay, that's clear enough. Right, let's go on to the other one. It says here all group 2 metals. These are alkali earth metals in as far as our periodic table. So this becomes your second column in the periodic table of elements from your left-hand side, right? They've got an oxidation number of +2. So group 1 +1, group 2 +2, in combined state once again. So what are we saying here? In this combined state, magnesium has a unit oxidation number of +2 because it is a group 2 metal. So there is some close correlation between group number for now and the oxidation number as far as metals are concerned. So group 2 +2 unit charge. So in this combined state, magnesium has a total oxidation number of +2. But then what about in magnesium nitride in this combined state or in this compound? The unit is +2. But then in this formula unit, we've got 3 of these +2. Then it gives us a total of +6, which is exactly how we arrive at the total oxidation number. Right, okay, let's move forward. What about oxygen atom in a combined state? Now, there's a difference between oxygen as a molecule of an element and oxygen in its combined state. So as a molecule of an element, that's the O2 part, because in nature, that's how it exists as a diatomic, molecule of an element. Why are we saying element? Because these are atoms of the same kind that are chemically bonded together. But in a combined state, we are talking of oxygen while it is in a compound. So take note of the difference. So as a molecule of an element, its oxidation number, unit oxidation number it's 0, but in a combined state, that's what we are focusing on. So in a combined state, it's -2. Take note of that. So in magnesium oxide, it's a practical example of oxygen in a combined state. So in this case, oxygen will always be -2 because there is only one of them. The total for oxygen is -2. What about in aluminium oxide? The unit is -2, but in aluminium oxide, there is 3 of these -2, which gives us the -6. Hopefully it makes sense. So that's very, very straightforward once again. Now, we can also talk about exceptions. There are a lot of exceptions in chemistry. So we are saying in combined state, it is always -2, except in a peroxide. A peroxide, for argument's sake, this is hydrogen peroxide as an example, okay? So this is our hydrogen peroxide. In this peroxide, we are saying it's the only exception. The oxidation number of the unit oxidation number of oxygen is -1. So this is an exception. So when we talk of exceptions in terms of the applications of the rule, we say, yes, the rule holds for everything besides when oxygen is in a combined state of a peroxide. So the rule applies to everything else except the peroxide. That's what we mean by an exception, right? Okay, and then hydrogen atom in the combined state has a +1, right? It's a given. So in this combined state, hydrogen is part of a compound, hydrogen bromide, HBr. So the unit is +1. Now, how many hydrogen atoms are there in this molecule? We are having 1. So the total oxidation number for hydrogen is +1. Okay, what about in a water molecule, right? The unit is +1, but how many atoms of hydrogen do we have per molecule of water? There's 2 of them, while each one of them is +1. So the total oxidation number becomes +2, which is how we get to that, right? Okay, now, there is also an exception here in as far as hydrogen is concerned. So in combined state, hydrogen is always +1, except in a hydride. So a practical example of a hydride is sodium hydride, right? Sodium hydride. Okay, what's up with the exception? What is it that is important? In a hydride, hydrogen will be -1, and it makes sense because we are saying that if sodium, which is a group 1 metal, there is no exception, all group 1 are +1, okay? And then the total for this compound is 0. Then it means, if the total is 0, it means here for hydrogen, it has to be -1. So that if we say +1 -1, we get the 0 that we're talking about, because this is a pure substance. We said the first rule that a pure substance or a compound, which is an element, will have a total oxidation number of 0. Right, so that's the exception. Okay, now the sum of all oxidation numbers in a neutral molecule or a compound is equals to 0. This is what we mean, that if in this case the unit for hydrogen is +1, okay, but there is how many hydrogen per water molecule? There is 2. Okay, now for the total oxidation number, then the oxygen in this combined state, because it's not a peroxide, is going to be -2. All right, this must actually give us 0. Right, so this is how we get the 0. The +2 -2 will give us a 0. So this rule says sum of all oxidation numbers in a molecule or a compound is equal to 0. Right, okay, and then this rule is used to find the oxidation numbers of other elements. In this case, we can try and find the oxidation number of sulfur in this hydrogen sulfide. So we are saying for hydrogen, it's +1, but there's how many of them? It's 2, okay, which gives us a total of +2. is equals to 0 because this is a compound, right? We are saying the sum of all oxidation numbers in a neutral compound. This is a neutral compound, is equals to 0. So what is the oxidation number of sulfur in this case? For us to get 0, this is going to be what? Minus 2, right? Because if you say 2, this will give us 2 plus 1 times 2 will give us 2 minus 2. So it means in this case, the oxidation number of sulfur is negative 2, right? So we can say here negative 2, and then the sum is negative 2 to give us 0, right? Okay? And then we can also use this rule in many cases to find even those of the polyatomic ions. Now, the sum of oxidation numbers of all atoms in an ion, okay? Which ion are we talking about here? Is the sulfate ion, SO4 2 minus. Okay, so the sum of oxidation numbers of these is equals to negative 2, right? Where is this negative 2 coming from? It is actually the net charge on the ion, okay? So what are we saying? Let's say for argument's sake, we want to find the oxidation number of sulfur in this case. We don't know what it is. Then we are saying minus 2 for oxygen. That's the unit oxidation number of oxygen. But there's 4 of them, okay? This total must give us what? Negative 2, okay? Which is that. And then this is for oxygen, right? What about for sulfur? We don't know for sulfur. So whatever we add to this, it must give us negative 2, right? So in other words, what is it that from what we subtract 8 to get negative 2? So if we go, if we go back, we can say, okay, let that of sulfur for argument's sake be X for argument's sake, okay? Then we are saying this is for oxygen, okay? Let me just erase that so that we can lay out our work nicely. Right, so we are saying that this is for sulfur, it's unknown, which is equals to, okay, minus 2 plus 8. Okay, I've just modeled this into a simple equation. So this for sulfur in this case, it becomes what? Plus 6, okay? So if we say plus 6 plus minus 8, we'll get the negative 2. Okay, so we use this rule of saying oxygen is always negative 2, except it's a peroxide, and also that the sum of oxidation numbers of all atoms in an ion is equals to the charge of the ion. And the charge of the ion in this case is negative 2. So this is the charge of ion, okay? Right, because this is a polyatomic ion, right? Okay, folks, we'll take a short break for now. See you after the break. Welcome back to our session. We're still talking about oxidation numbers. Now, we've taken time to actually look into, the different rules that we need when we actually apply, these rules of assigning oxidation numbers. But now we want to use practical examples, to try and apply these rules and see how exactly we put them into, practice. Right. So application of these rules for assigning oxidation numbers. Let's consider a substance like hydrogen sulfide. Now, first things first, hydrogen sulfide is a pure substance. What is a pure substance? A pure substance is an element or a compound. And immediately we talk of an element or a compound as a pure substance. What does the first rule say? It says to us that the total is equals to 0. So if you've got an atom of an element, the oxidation number total is equals to 0 for that particular substance. While again, if we have a pure substance in the form of a compound, the total oxidation number for that substance is equals to 0 as well. So that's our point of, of takeoff, right? So we want to find the oxidation number of sulfur in hydrogen sulfide, okay? Now let's go through the rules and how we best apply them and try to understand that specifically. So hydrogen sulfide is a molecule, right, of a compound. We are fine with that. As a result, the total of all oxidation numbers is 0. That's our first rule that we have to recognize in this case, right? So we'll assign oxidation numbers to each unknown atom in the compound. So total is equals to 0. That's what we know by now, right? And then what else? We are saying the hydrogen atom, because there's a specific rule that talks about the hydrogen atom. So any hydrogen atom, except in a peroxide, we are saying, in a hydride rather, we're saying that it has got an oxidation number of +1. So the unit oxidation number of hydrogen is +1, right? Now in this molecule of a compound, there are 2 hydrogen. So if we multiply 1 by 2, you'll get the total oxidation number for hydrogen as +2. So if the oxidation number of sulfur is unknown, what is it that we know by now? We know the total oxidation number, or we've managed to come to the total, or to get the total oxidation number of hydrogen. We also know that hydrogen sulfide is actually a pure substance, which is a compound. So the total for this compound is 0. So the one for sulfur, if we are going to say +2, plus whatever must give us 0, it means the oxidation number of sulfur is equals to -2, right? So that's how we apply that rule. Okay, now if we assign that, then the unit for sulfur in this case is equals to what? 2, right? -2, but there's only one of them. So if we say -2 divided by 1, okay, it doesn't change anything. It still gives us the total oxidation number of sulfur, which is equals to -2 in this combined state. So the unit oxidation number of sulfur in this case is equals to the total, because there's only one atom of sulfur per molecule of hydrogen sulfide. Okay, that's very interesting. Right, now we move on to the other one. We want to determine, by way of applying these rules, the oxidation number of nitrogen in nitrogen 4 oxide. Okay, so we want to obtain that. So this is nitrogen 4 oxide. What are we saying here? We've got N2O rather, okay? Right, so we want to understand that in this molecule, because this is a compound, now the total is equals to 0, right? So if the total is equals to 0, and then what do we know? We know that the unit oxidation number of oxygen in its combined state is -2, right? Okay, so if it's -2, but then we know that if there is only one oxygen, the unit oxidation number of oxygen actually equals to the total oxidation number, right? So if we talk about nitrogen, okay, there is 2 of nitrogen here. So what are we saying here? We are saying in this case, the total for nitrogen, for us to get 0, it means the nitrogen must be +2, okay? Right, this +2 is for the 2 atoms. So this is the total for nitrogen. And then it means the unit oxidation number for nitrogen in this case is equals to +2 divided by 2, which gives us +1, okay? Why? Because the +2 is the total for nitrogen, okay? Meaning that in this case, we've got 2 of them. It means each one of them is +1, right? So that's how we apply the rule. And then we've got a polyatomic ion, which is the dichromate ion, right? So the name of this ion is called the dichromate ion, right? Okay, so we want to apply the rules. So when we have a dichromate ion, we know that the charge on the ion is equals to the total of all the atoms in this polyatomic ion, okay? So the total, if we can take, for argument's sake, the formula Cr, okay, 2O, okay, 7, and then 2 minus, okay? We know that the total in this ion is -2, right? And then for oxygen in its combined state, the unit charge is -2. Right, so if there is 7 of them, we're gonna get -14, okay? So -14 actually comes from -2 multiplied by 7. So the total oxidation number for oxygen in this combined state is negative 14, while the unit charge is what? It's actually negative 2. So for us to get the one for chromium, we know that the total is that it should be negative 2. Then in this case, what do we have? We have got, let this one be x for argument's sake, okay, because we don't know it. You can even model it that way. So we'll have 2 times whatever the unit of, so this x is the unit oxidation number, right? Which is what we are looking for, right? Plus 14, it should give us the negative 2. So if we simplify this, we'll get, if we transpose that, it's going to give us what? Minus 2 plus 14, which is 12. Okay, positive 12. Okay, positive 12. Okay, so this positive 12 is actually the total. So in other words, we are saying that if we can put it in a simple way, this is plus 12. So this plus 12 is the total, right? So if the total is plus 12, so the unit oxidation number of Cr in this case is plus 12 divided by 2, which is equals to plus 6. That's how we have used the rules to actually obtain that. Because if you say plus 12 minus 14, it gives us the negative 2, right? And then last but not least, we have the manganese 4 oxide, right? So in as far as manganese 4 oxide, you do realize that this is manganese 4 oxide, this is potassium permanganate. So all of them are compounds. So in as far as Mn, let's say K, MnO4, this is potassium permanganate. The total is equals to 0, okay? The unit for oxygen is negative 2, right? Potassium is group 1, plus 1. Then we are looking for that. So the total for potassium is plus 1, okay? We don't know for manganese. For oxygen is negative 8. The total from negative 2 times 4. And then what is it that we do to this so that we get 0? It means it is plus 7. So the unit oxidation number of manganese is plus 7 in this case. What about in manganese 4 oxide? MnO2, right? So the unit for oxygen, negative 2, right? And then the total is 0, because this is a pure substance, which is a compound. So in combined state, oxygen is negative 2, but there's 2 of them, so the total is negative 4, right? Then in this case, to get 0, what must we do? This is plus 4, okay? So the oxidation number of manganese in this case is plus 4. You do realize that in this compound, potassium permanganate is plus 7. In the other one, manganese 4 oxide, it's plus 4. This is a transition metal. Its oxidation number can change, all right? That's what is so special about transition metal. So in closing, we are saying that atoms of the same element can have different oxidation numbers when they bond differently with substances. Okay, so these are some of the examples in as far as applying the rules for assigning oxidation numbers. We shall take a short break for now. When we come back, we'll look at more practical examples so that we can apply these rules. Let's take a short breather for now. Welcome back to our session. We're still talking about the application of rules in terms of oxidation numbers. But now we want to try and keep track of the changes in oxidation numbers that occur when a reaction takes place, and try to make sense of the big question that we're going to actually pose, right? So we are going to look at redox reactions now, right? And in the context of oxidation as well as reduction have reactions, but we shall try and arrive at the processes of oxidation and reduction with reference to oxidation numbers of a particular substance in a reaction, right? So the big question now that we want to pose is that have you ever thought about exactly what happens, what does a change in oxidation number tell us about the substance in a reaction. So in a chemical reaction, there is a lot of changes that happen in terms of the electrons of the substances that are forming, the atoms that are forming new substances when we form product. So we want to try and find out what happens in terms of oxidation numbers when a typical reaction does take place, right? So that's the big question for now. Now we shall look at the context of combustion of magnesium. So combustion is actually, put simply, a process which involves the burning of a substance in a lot of oxygen. Okay, so this reaction happens completely, or this reaction will only take place until all the magnesium in this case has burned. So we're told that we consider a reaction involving burning a piece of magnesium ribbon, which actually burns with a very bright flame, okay? And then this magnesium ribbon burns completely, all right? Now, here's the balanced equation of reaction between the reaction between magnesium and oxygen to give us a product, which is magnesium oxide. Okay, so what do we know? We know that neutral atoms or molecules formed an ionic substance, which is magnesium oxide. So this is a formula unit of magnesium oxide. Now this formula unit is actually based on a cation and an anion of magnesium 2+. So where does this magnesium 2+ come from? Let's go back to our rules of assigning oxidation number. We ask ourselves, okay, magnesium as a pure substance, in which group does it occur in the periodic table? We find it in group 2. So in terms of the rules of assigning oxidation numbers, all group 2 elements have an oxidation number of +2. Hence we are saying the formula for the cation of magnesium is 2+, which in this formula unit, which is a compound, right? And then the oxygen, always in a combined state, it's always O2-. So this is what we know by now, right? And then it goes further here and says, we want to apply the rules for assigning oxidation numbers to all the atoms in the balanced chemical equation, which is what we have done. We are saying that in this magnesium oxide, right, the total oxidation number is equals to 0, right? The unit oxidation number of oxygen in its combined state is -2. So if there is only one oxygen, the total for oxygen is -2, okay? What about that of magnesium is +2, right? To give us a total of 0, okay? Right, and then also in terms of the rules or assigning rules for oxidation, this is a molecule of an element. We know that every molecule of an element has a total of 0, okay? And also what do we know? We know that every atom of an element, its oxidation number is equals to 0, right? So these are some of the rules that actually must come to mind, right? Okay, now here is the balanced equation of reaction. Now the balanced reaction, what does it tell us? It tells us about the stoichiometric ratio in which these substances react with each other. And always think about the mole. Then we are saying that 2 moles of magnesium reacts with a mole of oxygen to give us 2 moles of magnesium oxide. So the ratio is 2:1:2. So this is basically the stoichiometric ratio in which they react. What else are we saying? If we are to keep track of the changes in the oxidation numbers, we know that magnesium as an element has a unit oxidation number of 0, okay? While on the other side, in its combined state, we managed to derive that magnesium, because it's a group 2 element, a group 2 alkali earth metal, in its combined state, it will have an oxidation number of +2. So there is a change in oxidation number of magnesium from 0 to +2. That can only be explained in terms of the electrons lost by magnesium. And there's an electron deficiency. Immediately we start to talk about the unit oxidation number of +2. So how many electrons were lost? 2 electrons. So there was loss of electrons for magnesium, which caused the change in oxidation number from 0 to +2, right? Okay, now let's focus our attention on oxygen. Oxygen as a molecule of an element the total is equals to the unit oxidation number, which is 0, because it's an element, right? And then on the other end, we have assigned oxygen -2, because it is in its combined state, okay? And this is not a peroxide, okay? So in its combined state, we know this rule that says it's gonna be -2. So the change in oxidation number for oxygen from 0 to -2, it means oxygen became electron rich by gaining 2 electrons. So there was gain, right? Okay. Now, if we are to, for argument's sake, look at the combustion of magnesium, you know, by making reference to the oxidation numbers, we've seen the changes that have taken place. Okay, so in the combustion of magnesium, there is a transfer of electrons from magnesium to oxygen. So this is the main point. What are we saying? When we talk about a transfer, there is some kind of a donor-recipient type of a relationship. So if somebody gives, somebody must gain. But whatever is given must be the same as what is gained for a transfer to be fair. Okay, so if in this case magnesium lost, whatever magnesium lost, oxygen should have gained the same amount. Okay, so that's the transfer, right? Okay, so this transfer of electrons is represented by 2 half reactions, which is our main point that we want to arrive at. So there's an oxidation half reaction which has to do with the loss of electrons. Okay, what does oxidation tell us? Okay, it tells us that magnesium changed its oxidation number while it was an element. Its unit oxidation number was 0. Okay, after the reaction, when the combustion had taken place, it became +2. Okay, so the reason why it became +2 is because it lost 2 electrons. So if you check, the 2 electrons are actually the negative charges that were actually lost. Okay, so if we can just to correct that. Okay, we are saying that. Okay, that's the pen. All right. So this is -2 for oxygen. So this, if you say -2, okay, +2, it gives us that 0. Okay, so it means magnesium lost electrons from an oxidation number of 0 to +2. Okay, and then also we are saying the opposite happened to oxygen. There was a process of reduction. The oxidation number decreased. Okay, when the oxidation number decreases, it means the substance has gained electrons. Okay, so it became more negative or less positive. While that of magnesium became more positive, there was an increase in the oxidation number. I think that's the main point. So the gain of electrons makes the oxidation number of oxygen to change from 0 to -2, right? So this is the gain of oxygen. And then this half reaction is referred to as a reduction half reaction, right? So the oxidation and reduction half reactions are very important in as far as the transfer of electrons. So in any reaction where there's a transfer of electrons, there is oxidation and reduction taking place simultaneously. This is called a redox. So redox actually consists of that part, which is oxidation, okay? Oxidation, which has to do with the loss of electrons, okay? And then it also has to do with the reduction, okay? So reduction and oxidation is what gives us a redox. This one has to do with the gain, right? That's the main idea, right? And then a small coil of copper wire is placed in a solution of silver nitrate. So we've got copper in a solution of silver nitrate. After a short time, there is an observation that is made. The solution turns blue in color, and silver, a white deposit appears on the copper. Okay, so this is what it looks like. Okay, so if we've got a copper wire, you can see the copper wire there, right? And then it is placed in a solution of what? Silver nitrate, okay? Chemical formula, very, very important, right? And then we've got our copper there. That's our copper wire, okay? Right, this is the observation that is made. And then in terms of the chemical equation that takes place, copper reacts with silver nitrate to give us copper nitrate and silver, okay? Identify the oxidation and reduction half reaction by assigning oxidation numbers. Right, what is clear here, Copper as an element, it has an oxidation number of 0. But on the right-hand side, when we trace copper, it has an oxidation number of +2. So what exactly happened to copper? Copper, if the oxidation number increased, it means copper underwent some loss of electrons to give us copper 2 plus 2 electrons. Okay. So for copper to change from 0 to +2, there was oxidation, okay, which is the loss of electrons, right? And then again, we can talk about silver. But what is important before we talk about silver, the nitrate is still the same on the left and on the right, okay? So we can immediately say, okay, if this is the half reaction for copper, this is what we got. We got copper, its oxidation number increased. It can only be explained in terms of the loss of electrons, okay? That's our oxidation half reaction. And then in terms of silver, in this combined state, we know the nitrate ion is -1. So silver in this case is +1, and then on the other end, it's 0, right? So we can immediately say, okay, what happened to silver? Silver underwent a decrease of oxidation number. In other words, it became more negative, or sorry, it became a less, it decreased from +1 to 0. So we can say Ag plus, okay? That's the silver on the left-hand side, which is the +1, plus an electron, all right? And then this gives us what? Silver metal, which has got an oxidation number of 0. So this is the oxidation half reaction, which has to do with the loss, okay? And then this is reduction, which has to do with the gain of electrons. So these are the big ideas, all right? So in summary, we are saying oxidation numbers are used to identify when electrons are transferred. So transfer has to do with loss and gain subsequently. And in a nutshell, we are saying reduction involves the gain, and then oxidation half reaction involves the loss of electrons. Right. So that's as far as the big idea of a redox reaction, which actually consists of both oxidation and reduction taking place simultaneously, wherein there is a transfer of electrons. We shall need more practice on this, so try to look into more and more problems that involve oxidation numbers so that we become comfortable. So that's the time we had for today. It's cheers and bye-bye for now.